so much, Keisha, and I want to thank the whole AstroTours committee for all the work that they've done to get this first in-person AstroTour in nearly 2 years running. It is a huge accomplishment, so thank you to all of them. And it is wonderful to see you all. I'm thrilled to be giving this talk. Just to check first, can everyone at the back hear me okay? Audio is good, thank you for the thumbs up. And can everyone see the screens okay, or should I dim the lights a little? Oh, we're good, excellent, okay. So, I'm going to be talking about a project that I recently wrapped up, in which I was searching for a really strange and rare class of stars, but as the title might suggest, there were some interesting twists and turns along the way. So I'll be giving you a little bit of broader context as to what it is I study before diving into details. And if I were to put it most generally, what I study is stars. Stars that you see in the night sky. Stars are the fundamental building block of our entire universe. They are the contents of our galaxies, they produce gas and dust, and they're the host of planets like our own Earth. Lots of different types of stars exist, and by studying populations of stars, especially those that are maybe rare or unusual, can give us a wealth of information not only about stars, but about the universe as a whole. So when you look at a huge range of stars like this, with different brightnesses and different colors and different properties, how might you go about organizing them? Well, astronomers have one way, a diagram called a Hertzsprung-Russell diagram, which I'll walk you through right now because it's a really good way to get a broad sense of stellar astronomy. So we begin with temperature on the horizontal axis. And in astronomy, red stars are colder. If you think of heating up a metal, it can get red hot, but then the hotter you go, it can get white hot and even blue hot. And in astronomy, we have the colder, redder stars on the right side, and temperature increases to the left. And then on the vertical axis, we have luminosity, where this is another way of saying the brightness of a star. You can think of it like how many watts the star puts out, like if it were a light bulb. And there are dimmer stars on the bottom, and increasing brightness as you go up. So on this diagram, I will put our own sun. Our sun is a pretty typical dwarfed star. And when I say dwarf, those are stars that are burning hydrogen into helium in their core. And this is where most stars spend the majority of their lives. So most stars will be in the same area as the sun. And if I add more stars to this diagram, you'll see that dimmer stars are typically redder, and hotter stars are typically brighter. And when you put all of the dwarf stars on your general diagram, you get this really nice line, this diagonal line, and we call this the main sequence. So main sequence stars, or dwarf stars, are those that are going through this majority portion of their lives. However, stars, including our own sun, will eventually run out of the hydrogen fuel in their cores. But that's not quite the end of their life just yet. Our sun will, once it runs out of hydrogen, start burning hydrogen in shell around the core. This will cause our sun to start to grow. It'll become colder, but it'll also swell up. The surface area increases, so it'll get brighter, and it will become a red giant star. And stars that are in this area of the Hertzsprung-Russell diagram are known as giant stars. And in particular, when you get the oldest, most close to the end of their life giant stars, they're in an area called the asymptotic giant branch. A little bit of a weird word. It refers to the fact that the evolutionary track of these stars goes straight up when it gets to this point, so it's asymptotes. But if I say AGB star, you can just think stars like our sun that are really old, really close to the end of their lives. And of course, there are more stars than just those like our sun. There are massive stars, stars that have a lot more mass and weight than our own sun. Those will take a different evolutionary path. They'll still become brighter and become cooler, but they will go across the top of the diagram, and they will become what we call supergiants. So a red supergiant that you may have heard of, for example, is Betelgeuse, one of the most famous, and you can see it from Toronto. So these are much bigger stars than our own sun, and they become much more luminous. Now, if you take a Hertzsprung-Russell diagram, you can sort of broadly divide it into 4 categories. It'll be useful to go over some terminology. You can divide it into main sequence stars and evolved stars. So when I say evolved, it means that they've evolved off of the main sequence. And this includes both giants and supergiants. They're both older stars. But the second way you can divide it is into low-mass stars and high-mass stars, where low-mass stars become giants and high-mass stars become supergiants. So that's one of the ways that you can make use of this diagram. I'm going to change it now to a slightly prettier artist impression. You might recognize some of the names of stars. So while stellar astronomy is one of the oldest fields in astronomy, there are still lots of open questions that stellar astronomers have. And I'll just run through a few of them now. For example, how far down this diagram can you go? How small can you make a star and still have it be able to ignite nuclear fusion and shine? Another question on the exact opposite end, how big can you make a star? It can't actually go on forever. And in fact, when clouds of gas are collapsing to form stars, there's a little bit of a predisposition for big chunks to fragment into smaller chunks. So it's more common to get low-mass stars than it is high-mass stars. So this question of what is the limit, is it 100, 300, 500 solar masses? I'm not quite sure. And now, if you consider the evolutionary path of stars, as I mentioned before, stars like our sun will evolve into giants. They will eventually shed off their outer layers, leaving behind a beautiful planetary nebula, and right in the middle, a white dwarf star, which is what is left at the core of that giant. And if you consider supergiant stars, they will eventually burn up to really heavy elements, including iron, but they'll be unable to support their envelope, which will crash back down and ricochet out in a violent supernova explosion. This also leaves gas and dust into the universe, but it does it in a very different way than giant stars. So if you were to look at a star like our sun, 1 solar mass, you can be very confident that it will become a planetary nebula and a white dwarf. And if you were to look at a 50 solar mass star, you can be very confident that that will blow up as a supernova. But one question is, where is the tipping point? Where do you stop having giant stars and start having supergiant stars? This exact tipping point is another open question in the field and has some important consequences. And finally, one of the most important aspects of stellar astronomy, and one that has been given a lot of study in recent years, is binary star systems. If you're a fan of science fiction, you probably know one binary star system quite well. And so a binary system is when you have two stars orbiting each other. And these stars can interact, they can exchange mass, they can even merge, which is something that I'll be talking about in a moment. But this is just a broad view of some of the questions that astronomers have. So then, when we have these questions, what do we do about it? Well, we do as the scientific method was taught to us. Using our understanding, our previous knowledge, and physics theory, we'll formulate a hypothesis for some question. And then we need to design tests that allow us to figure out the answer to that hypothesis. But how do you do that? If I want to know the temperature of a star, I can't go out and stick a thermometer in it. I can't lift it up and put it on a scale and see how much it weighs. We're pretty constrained here. So, astronomy broadly, using the limited resources that we have, you can divide it into things like astronomy theory, which uses the fundamentals of physics to pose questions about the universe. Modelers and simulations who take theory and devise computer programs that will allow you to try and answer those questions. Then there are observers like myself who will look at stars and try to figure out, are the predictions of theorists correct, or is there something more that we don't understand? And then finally, there's instrumentationalists who make all the equipment that I use to do my job. So I'm going to be walking you through my project. And this project was about a very peculiar class of star called a Thorne-Zytkow Object, or a TZO, as I'll abbreviate it. This is a product of binary evolution, and in fact, it's a binary merger. Thorne-Zytkow objects are quite literally stars within stars. It is a red supergiant little evolved massive star that has swallowed a neutron star. Neutron stars are one of the possible remnants of the supernova explosion. So this is quite literally a stellar turducken. There is a whole other star inside of a red supergiant, which is fascinating and one of the most interesting things that I've ever heard about in astronomy. So you get this by having two massive stars in a binary system. One explodes and creates a neutron star, and through some complex physics, that neutron star can merge with the red supergiant and become a core. These objects were theorized in the 1970s by Kip Thorne and Zytkow, as per the name, and they had several theoretical predictions that might help us try to identify these stars. One of them is the mass of these objects. Theory states that TZOs have to be at least 15 times the mass of our sun. If they fall below that, they'll actually collapse. And figuring out if TZOs actually exist, and this has been an open question for quite some time, is really important because it will let us know if TZOs do exist, that is an avenue of binary evolution. If they don't exist, it cuts that avenue off. But how do we find them? So there are more predictions from Thorne-Zytkow's original theory. Now one of them has to do with the elements inside the star. So this is a really rough diagram of the Thorne-Zytkow object. There's the neutron star right in the center. There's the big red supergiant envelope, really puffy, mostly made of hydrogen. And then there's the thin atmosphere of the neutron star. And this atmosphere is incredibly hot, so much so, it is hot enough to ignite nuclear fusion. And because this nuclear fusion is happening right next door to a whole neutron star, strange elements are created in a Thorne-Zytkow object that are not created in red supergiants. And this solves a problem because from the outside, a TZO just looks like a red supergiant, especially when you're viewing it from hundreds of thousands of light years away. However, because the envelope of a red supergiant is convective, you can think of a convection oven, heat pulls things out to the surface. Elements like rubidium and molybdenum are just two examples. They are pulled to the surface of the star. And as I mentioned, you expect to see these weird elements from Thorne-Zytkow objects. You don't expect to see them from the normal red supergiant. So that's a way to identify TZO. But how do you do that? How can you tell what a star that is so far away is made of or what it has in its atmosphere? So if we think about light, stars shine, of course, they produce light. And if you think of white light being broken up into a prism, it spreads it out into all of its colors, like a rainbow. This light travels out of the star. And atoms of elements, any element at all, like rubidium and molybdenum, they can block or absorb particular wavelengths or colors of light. So when this white light, which has all the colors in it, comes along, it hits these elements and some of the light is blocked. So not every color makes it to our telescope. And every single element has a unique fingerprint of which colors it blocks out. So this is how we can tell which elements are in the atmosphere of a star. So this is a process called spectroscopy. And what we get in our study is something that looks like this. So you can see the spectrum here all laid out. On the bottom is just the intensity. And you can see there are areas where there are black bars or dips in the intensity. These are areas where elements have blocked these colors. So this spectrum here corresponds to some fingerprint of some element. So we can say that element is inside of the star. So we can look for Thorne-Zytkow objects in this way, looking for these strange elements. And in 2014, that is exactly what happened. Emily Levesque and her collaborators identified a star in the small Magellanic Cloud. That's one of the satellite galaxies of our Milky Way, kind of like in the Milky Way's backyard. That is really bright, really red, like a red supergiant, but the elements in its spectra are what you expect for a TZO. This is super exciting. And this star is called HB2112, and it's in this image. It's that little light right there. So spectroscopy is really hard and really expensive to do. So finding the star was literally like finding a needle in a haystack. But not quite that simple. HV2112 is a special star. HV2112 is not content being easy to explain. And as many things are in astronomy, the true nature of the star is debated. Other studies posited that HV2112, instead of being a Thorne-Zytkow object, was a giant star just like our sun would become. So one study thought that HV2112 had about 5 times the mass of our sun. This would make it a pretty large AGB star. There was another study, it didn't make a conclusive argument for TZO or something called a super AGB star, but it pointed out that a lot of the characteristics of HV2112 could be explained by something called a super AGB. And do you remember before, when I was talking on the Hertzsprung-Russell diagram about gaps in our knowledge, in particular, the tipping point between low and high mass stellar evolution? Well, super AGB stars, which are thought to be about 6 to 12 times the mass of our sun, those are the biggest giant stars. They are the last stars, the largest stars that will still evolve up the giant branch before you start getting supernova. Those are the tipping point. Those are also very interesting. And the original paper, of course, posited that this star is a TZO, which has to be bigger than 15 solar masses. So there's some disagreement here. And this is where myself and our collaborators came in. They have this problem. HV2112 has similarities to both Thorne-Zytkow objects and super AGB stars. Crucially, hilariously and also frustratingly, despite being totally different, TZOs and super AGB stars have the same elemental signatures in their atmospheres. It's through totally different processes, but it's the way that it ended up. So spectroscopy alone, while it's enough to tell us that the star is weird, it's not enough to tell us what flavor of rare star it is. So then we had 2 questions to try and solve this problem. And we decided to look at it from a little bit of a different angle, instead of just drilling down more on HV2112. We asked the question, is HV2112 unique, or are there other stars with the same properties? Then if there are other stars, that gives us a wider variety of stars to analyze, and maybe there'll be something there that can help us tell the difference. Which is the second question. If there is a population, can we put any constraints on their true identity? Can we say, conclusively, super AGB or Thorne-Zytkow object? So this was the start of my first project, and my hypothesis is essentially in the title. This was what I was calling the paper as I was working on it. A systematic, which just means we looked at all the stars basically, identification of Thorne-Zytkow object candidates in the Magellanic Cloud, those satellite galaxies. Keep the title in mind for later, might come back. So in order to explain more of the layer analysis, I'm not going to go into deep detail about how we found more stars like HV2112. I'll just say importantly, in addition to being bright and red and having strange elements, HV2112 is a variable star. That means that its brightness changes over time. It's like the star has a dimmer switch in it, and someone is turning it down and turning it up and down and up in a cycle over time. We thought that this was really interesting and really unique, so we looked for stars that had the same variability properties as HV2112. And we found a bunch. So this was really exciting. So this is the small and the large Magellanic Cloud. The blue circle here is HV2112. The yellow circles are 10 core candidates that really looked a whole lot like HV2112. The green triangles are other stars that we thought looked kind of similar, but not enough to warrant a deeper analysis. So we have 10 stars. So that answers the first question. But then the second question is a lot more complicated. What can we do to try and figure out the true identity of these stars? So what we did was we threw the kitchen sink at this problem. We did every single type of analysis that basically we could possibly think of in order to try and tell if there was any way to tell the difference between the two suspected identities of these stars. So I'm not going to go into detail for all of these because I would be here for like 6 hours, but I will go into detail for some of them. And I'll start with the variability and the color properties. So this is a version of a plot from my paper. On the horizontal axis, we have the variability amplitude. This is how much the brightness changes. So what's the difference in watts, essentially, between when the star is at its darkest point when it's at its brightest point, increasing up this way. And then on the vertical axis is the brightness of the star, but in a red filter, because all these stars are super, super red. And you can see in the top left, in violet, there are red supergiants. These are very bright stars, but they don't have a high amplitude of variability. The red circles are AGB stars. So these are lower mass, and you can see that the brightness is a little bit lower as well. But they have a huge variety of big amplitude and their variability. HE212 is again in blue, and the rest of our candidates are in gold, and they're kind of in the middle. They have brightnesses that are similar to red supergiant, which is what you would expect with these of those. Super AGB stars are also supposed to be bright, and they have variability that matches AGB stars. Unfortunately, there aren't modern models of Thorne-Zytkow objects, so we can't say anything about the variability properties, but this is still a good first step. So I mentioned before that spectroscopy, they can't really help us tell the difference. However, it would still be really important to know, do the rest of our candidates have that same elemental signature that HE212 has? So this allowed me to go observing and gave me the huge privilege of being able to travel to Chile to go to the Magellan telescopes at Las Campanas Observatory. These are 8.5-meter telescopes. This is one of the domes. And these are two of the domes in the night sky. It's a little bit hard to see, but there's a bright patch up top. That is the center of our galaxy. You can see it with your naked eye when you are down there. That is how dark it is. It was a very incredible experience. This is sort of half of the telescope with a meter scale. It literally can't even fit in the shot. So as I said, these are 8.5 meters wide, and they're absolutely gargantuan. I thought I had an idea of how big it was. You know how you think you know how big a moose is, and then you actually see a moose and you're like, oh. That's how it is for this telescope. It's gargantuan. And this is me inside of the control room. So this is where we actually do our work. And just off to my right, with about 3 times as many screens in front of him, was our telescope operator. So these are expert technicians who know how to operate and fix this multi-million-dollar gargantuan machine. And we would be absolutely lost without their technical expertise. The telescope operators are how we do our work, so we're very thankful for them. So, as I said before, the spectroscopy, it should be the same for both. There's an asterisk there because the spectroscopy is really complicated. If anyone wants me to go into detail later, I'd be happy to chat more about it. But for now, just know things checked out. We saw the elemental signatures that we were expecting. I'm going to end off in terms of the analysis, coming back to the Earth's Variability diagram, to talking about the brightnesses and temperatures of these stars, and the mass. Because if you remember from before, Thorne-Zytkow objects have to be 15 times the mass of our sun or bigger than that, whereas super AGB stars are between like 6 and 12 times the mass of our sun. There's a little bit of a gap there. So if we can figure out a way to estimate the mass of these stars, which is very difficult to do, but if we can, that might be a way to tell. So coming back to the Earth's Variability diagram, if you consider the evolutionary paths that stars take in this diagram, the massive stars will go along the supergiant branch, blowing up into red supergiants, whereas stars like our sun will go up into the giant and later the asymptotic giant branch, or the AGB. Now I want you to just focus on this part of the diagram, just the part where the oldest giant stars, the oldest AGBs, and the oldest supergiant star. I'm going to blow it up, and I'm going to switch it out with a more technical plot from my paper. But if you pay attention to the green lines and the blue lines, you'll be able to see them again in this picture. So this is the exact same thing. The green lines here are the evolutionary tracks of red supergiants. The blue tracks are those for AGB stars. And this cornucopia of color over here, this is where our candidates lie. It's a little bit blobby because as these stars are variable, their brightness changes over time, but they land in this area. That is nowhere near the red supergiant tracks. And if you remember, right is colder on this diagram, so they're way too cold compared to red supergiant. And they seem to line up with the models that we have available. Stellar modeling is really hard, and high mass AGVs are particularly hard. But they generally line up with that. So this is super interesting. However, there is theory that Thorne-Zytkow objects might be able to be a little bit colder than red supergiants. So maybe this doesn't rule out Thorne-Zytkow objects. And in particular, we're kind of missing something from this diagram. First of all, we're missing two things. The AGB tracks only go up to 6.5 solar masses, but we think that super AGBs are 6 to 12 solar masses, thereabouts. We're not models of TZOs that we could realistically put on this plot. And this is a problem because we want to see if the physical properties of these stars line up. However, one of our theorist collaborators had a really clever idea to solve this problem. If you look very broadly at the structure of a Thorne-Zytkow object, it has a big convective envelope, that's the red supergiant envelope. And it has an incredibly dense neutron star core. Neutron stars are so dense that a teaspoon of neutron star material weighs more than the Rocky Mountain chain. So they're extremely dense. Super AGB stars also have a big, fluffy convective envelope. Their cores are what would eventually become a white dwarf once the outer layers pop off. It's made of oxygen and magnesium, but more importantly, it is also very dense. It's not as dense as a neutron star, but it's still very dense compared to the rest of the star. So if you don't squint too hard, to first order, these are roughly the same. TZOs and super AGBs are both stars with really dense cores and really big envelopes. And crucially, the variability of a star, when a star is variable, it is literally pulsating. It's getting bigger and it's getting smaller as waves propagate through the convective envelope. And the way that those waves propagate is directly related to the structure of the star. So what our theorist collaborator basically said is that we can take the AGB models that we already have, steal their structure, how they basically work, and then just scale up mass. We can scale it up to 12, and we can even scale it up to 15. We would have a really rough model of a star at any mass that has a dense core and a fluffy envelope. And this should be broadly the same for both super AGBs and TZOs. We can put them on the same diagram. And this is the last diagram that I'm going to walk you through, and it's really important, so I'm going to go through it step by step. So on the horizontal axis, we have the period of the variability. So when a star is pulsating, this is how long it takes to go from bright down to dim and then back up to bright again. Complete one cycle. And on the vertical axis, it's the radius of the star, which is how big it is. Here, because of the structure constants and the pulsational properties that I was telling you about earlier, we can relate those two variables to mass. What that means is that we can have lines of constant mass on this diagram. So when I say constant mass, I mean if you were a 5 solar mass star, anywhere along that line, that is where you will live. Whether you're a smaller star with a smaller period or a bigger star with a bigger period. If you have 5 solar masses, that's where you're going to be on this diagram. If you have 10 solar masses, you're going to be there. If you're a huge star, if you're above 25 solar masses, you'll be up in the top. So using properties that we already know for the stars, we can get an estimate of their mass. And crucially, the area that I just shaded in, that is the safe zone for Thorne-Zytkow objects. If you think a star is a TZO, which was our hypothesis, it had better be up there because it has to be bigger than 15 solar masses. Then I'm going to put our stars on this diagram. They're going to be long ovals because remember their radius changes as they pulsate, but you can get an idea of the mass. They're not in the safe zone. All of them, and I will crucially point out this blue one up here, that's HV2112. That's a prototype. None of them are in the safe zone. They are all too small to be Thorne-Zytkow objects. However, if I were to put the mass range for super EPP stars on this plot, well, some of them are a little bit small, maybe 4 or 5 solar masses, but a bunch of them, and if you take the average radius, especially HV2112, they line right up where they're supposed to be for being super AGV stars. So, looking at the final diagram, I filled in all the other areas. You can see everything is green for super AGV stars. So when I saw that plot for the first time, I was like, oh, can't configure that anymore. That's not right. The conclusion changed, or not the conclusion, my hypothesis was proven incorrect by the conclusions of the data that we have. This is what the paper is actually called. Cool, luminous, variable stars in the clouds, implication for Thorne-Zytkow objects, and super AGV stars. So this was super strange, especially since this was my first PhD project. To just have it go completely sideways was kind of hilarious. But recognizing when our data tells us that our hypothesis is wrong is, to be honest, the crucial part of science. We follow the data where it leads us, not necessarily where we want it to go. And this is why, especially in more public sciences, scientists might appear to change their minds. But that's not exactly what's happening. It is acknowledging and accepting new information, new data, and our new insights as they come. So even though this is a little bit of a weird thing that happened for my first project, I'm actually quite glad that it happened because it was a very good learning experience. Now, super quickly, I'm going to tell you why super AGV stars are still in fact really cool. So it wasn't disappointing that we didn't find TZOs. So as I mentioned before, super AGV stars are this tipping point between low and high mass stellar evolution, between stars that will become planetary nebulas and stars that will blow up as supernova. And if you look at all the elements in our universe, they come from different places. This excellent diagram shows you where, but crucially, all of the boxes that have yellow on them, those elements are made in planetary nebula, so they come from giant or low mass stars. And the green boxes are ones that are spread out into the universe when a big supernova blows up, or from high mass stars. And as I previously mentioned, there are more low mass stars than high mass stars generally. So if you think about the mass of stars, you can see with 10% the mass of our sun, 10 times, 100 times the mass of our sun. And just if we look at like all the stars in our galaxy, how many are there? This is the shape of the curve that we'll see. So there's way fewer 100 solar mass stars than there is 1 solar mass star. And this is where super AGV stars are important because we don't know where the switch-off point is between low and high mass stellar evolution. So finding a population of these stars, and there was one candidate before I finished my research, and with the, I'd say 7 or 8 that I'm really sure are super AGVs, that is now a population that can be studied and compared to theory. But if you think that supernova start at 8 solar masses, then you have the yellow part, the yellow elements on the left and the green elements on the right that are created. But if that's wrong, if studying super AGV stars tells us no, supernova actually go off at higher masses, at 12 solar masses. Because there are more low mass stars, that dramatically changes the ratio of the yellow elements to the green elements. So it changes what the makeup of the universe, what we expect it to be. So that is why super AGV stars are just as cool. So that brings the science portion of this to a close. We can put constraints on the identity. Some of them are a little smaller, but some of them are super AGV stars. So if we go back to the Hertz-Barroso diagram, this is about where they be, bridging that gap between the giant and the supergiant. So if I were to, I'm just going to put my name on the plot for a second, because this is where I do my work. mostly giant stars, mostly massive stars. I'm also now sort of in the gap, although that was accidental. I didn't plan studying for APDs. But I can also add other names to this plot of people who study stellar astronomy. And because, just one second, please, on your mouse here. Because it's Pride Month, I want to talk about other queer astronomers. And I want to thank Kate Story-Fisher of AstroTours for compiling a lot of the information that I'm going to talk about. She has a really good article about queer astronomers. So Dr. Frank Kameny, he was a student of Cecilia Payne Gaposchkin, who is renowned in the stellar astronomy field. He completed his PhD in 1956, and he studied yellow giant and supergiant variables. He studied variable stars, just like me. He taught astronomy at Georgetown University for a little while, but then he ended up working for the U.S. Army Map Service. And in his job there, he was accused of being gay, and because he wouldn't respond to the questioning, he was fired. After this, he turned to activism, and Frank Kameny is one of the most well-known queer activists in American queer history. He fought to have the designation of homosexuality removed as a mental illness and succeeded. He organized one of the first queer protests at the White House, and he actually coined the slogan, "Gay is good," from this time period. So, unfortunately, while Frank Kameny was not able to be his authentic self, his astronomical contributions were still really important. There are other astronomers from this time period as well. Dr. Neil Devine pioneered work on helium stars, which are stars that have lost all of their hydrogen envelope, and he worked with Carl Sagan. And there are also queer astronomers in other areas of astronomy. Dr. James Pollack studied the atmospheres of Mars and Venus, and later moved on to be one of the most important contributions to the Mariner missions at NASA. And you may know Sally Ride as the first American woman in space. She is also a queer astronaut, and she completed a PhD on the interactions of X-rays in the interstellar medium. So these are just the names of a few queer astronomers. And I also want to highlight the research of, just one quick second, sorry, I'm having a break. Okay, I'll do that. Also want to highlight the names of modern queer astronomers, such as Dr. Josby Jenda. They study neutrino physics and how it interacts with multi-messenger observations of supernova. You remember the neutron star merger that happened a while back? That's multi-messenger astrophysics. Dr. Sarah Dawson studies things like gamma ray bursts and magnetar flares. Daniela Marone, they study exoplanets. So planets like our Earth but are around alien stars. Dr. Alana McDonald studied gravitational waves coming from black hole mergers, which was the first LIGO detection was in 2015. And Simran Naval and Dr. Renee Hlajek studied cosmology, cosmological inflation for Simran, and Dr. Renee Hlajek told me to say that she studies what makes the universe tick, which is really cool. So this is just a small sampling. These are mostly people from UofT. And while a tremendous amount of progress has been made since the time of Dr. Kameny, I do want to acknowledge that there are still many members of the queer astronomy community who are not out. There's no time limit on coming out, and some people just aren't quite sure yet, which is fine. But many students, researchers, and even professors are in situations where coming out would have negative or even dangerous consequences for them. This can particularly be the case for queer astronomers who are not white and astronomers who are trans or non-binary. However, Pride Month is for all queer people, whether you are out or not. So those are what those boxes represent. However, due to the activism of many people, from Dr. Frank Kameny up to people in the present day, being out is an option for many queer astronomers. And I like to think that Dr. Kameny would be really happy to know that there's something called the Astronomy Out List that exists. This is a public website that anyone can go on, where astronomers can put their name on it, queer astronomers, and there's also a list for allies that basically flags you saying, I want to be a role model, I want to be a point of contact for other astronomers who might need someone to reach out to. I did not take all the names from this, because if I did that, my laptop would have exploded with all the text. So this is just a small sampling of what is on here. But I just wanted to highlight how big, how diverse, and how beautiful the queer astronomical community is, just how many names there are. A lot of these people are professors, but a lot of these people are also grad students, undergrads, technical instrumentationists, public outreach. Someone here is an assistant director of the Hayden Planetarium, which is very cool. Yeah, so I just wanted to show this slide because it's important and it's relevant. So thank you all for listening. This is a list of all the people who helped me do these projects. I would not be able to do it without these people, particularly Maria Drought and Brian Kingsler, who are my supervisors. And I will be happy to take questions, and thank you. So, 4 questions. If anyone has a question, you can raise your hand, try to project, and I will repeat the question back so everyone in the audience can hear. But I'm happy to take any questions.
I have a question. So, if you started your research looking into TZOs and then realized that you were maybe looking at the supergiants, was this sort of a gradual realization, or was there like a moment where graphing out you went, oh crap, it's all different?
That's an excellent question. So the question was it a gradual process for me realizing that what I was actually looking at was super AGVs, or did it happen kind of suddenly? I would say it's something of a mix. I was really on the TZO train, and I presented preliminary results at a conference in Baltimore, and Dr. Carolyn Doherty, whose name is up there, she is an expert theorist in super AGV stars. And she came over and she was looking at my work, and she was like, you should really look at the super AGV side of this. So that is what convinced me to start thinking about ways that we could really tell the difference a little bit more, particularly the mass. And then Jim Fuller, who's also up there, was the one who came up with the mass designation. So I was thinking about it for a little bit of time, but I literally did have the moment where I was like, oh my god, I need to change the paper name. And that's when that mass plot happened, where everything is below the line. So I guess, great question.
So for that mass plot with the lines, you have the variability of the power emitted by the star, light, right? What determines that? Well, two questions. What determines the intensity of the light? Is it the physical shape of the star, like how large it gets, or is it some convection process inside?
That's
Some chemical process inside.
That's a great question. So asking in terms of the variability of these stars that I'm looking at, what causes the changes in brightness? And it is the first thing that you said, which is the physical size of the star. So most variable stars are what we call pulsators. So you can think of blowing a balloon up and then letting a bit of air out and blowing up again. The physical size of the star is literally changing. So that will cause it to, as it gets bigger, it will cool down a little bit because its atmosphere spreads out a little bit more. However, the surface area of the star gets larger. And the mathematical relationship works out basically that the surface area change is more important than the temperature change. So as it gets big, it will get brighter, and as it falls back down, it will get dimmer. So it literally is, it's like the difference between, if I had a light bulb that was this big, and I swapped it out for a light bulb that was this big, even if the wattage was the same, this light bulb looks brighter.
On the objects that you were saying before, I can't remember the name. What would happen if it was a pulsar neutron star that was absorbed by a red giant? Are there any theoretical models for that or no?
That is an excellent question. So the question is, what would happen if a neutron star that was a pulsar was the thing that was swallowed by the red supergiant? I'm not exactly sure, so I'll just briefly explain what pulsars are. So neutron stars spin, and they spin very, very fast. And some neutron stars will accrete, and they will essentially have these jets of energy, these beams that are coming out at either end. And pulsars are what happens if the axis of rotation for that neutron star is in our line of sight. So the jets are like whirling towards us and whirling towards us, and we see this like doop, 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 doop signal. In terms of what would happen if a red supergiant ate that, I'm not actually super sure. That's a really good question. Pulsar jets are pretty energetic. So what I imagine might happen when the neutron star is first swallowed by the red supergiant, it has to make it through the envelope and get all the way down to the core, the heart of the red supergiant. And I think if the jets injected enough energy into the envelope, new energy that wasn't there before, it actually just blow the envelope off. And then I think what would happen then, you would basically strip the envelope off of the red supergiant to be left with the core of the red supergiant, or maybe not the core, just a smaller envelope, and the neutron star in a much tighter binary than was there before, but it doesn't totally swallow it. Wait, excellent question. And I think someone behind you have a question? Yeah.
What you were saying earlier about a star like pulsing and like expanding and tracking, like over what time period does that happen?
Yes, excellent question. So the question was, what time period does the variability happen over? So this can be different for many different types of stars, but for our stars in particular, their periods were about 600 days. So not quite 2 years. So it would be starting from when it got brightest. If you measure the time, if it went all the way down and got bright again, it would be about 600 days. So they're very long pulsators.
With respect to differences between the spectroscopy of these areas and super AGV, people are very similar. Is there any particles using enough to transmit your included interaction that maybe it's your portion of these or that you would say that we even like
I had run a slide for this exact question, thank you. So the question was, yes, it's up there. I said the spectroscopy was really the same, but there was an asterisk next to that. Is there anything that we can tell? These are plots directly from my paper, it's very complicated, but what I can tell you is that the thing that really stood out, this plot right here, this is molybdenum, so one of the things that you expect in TZOs. Most of the stars don't have it. That's okay for super AGV stars, because molybdenum is really heavy. It takes a long time for that element to build up. So it's okay for our hypothesis of being super AGVs that looks like that. But what's this guy up here? That's the most special star that ever was. That's HV2112. HV2112 just kept being the most all the time. So it has a lot of molybdenum, possibly even more than it has rubidium. And just to throw a huge spanner in the works, while for super AGVs you expect more rubidium than molybdenum because molybdenum is heavy, because the nucleosynthesis process for TZOs is a lot faster, it's a lot more violent, you can actually have, there's one paper that theorizes that you would get more molybdenum than rubidium, and that's exactly what's shown for HV212. The mass is then still a problem, but maybe there's ways that can be worked around. That 15 solar mass limit is a theoretical limit. It's based on things like things that astronomers don't have a super strong understanding of, like mixing or how convection works in stars. It's possible that that limit, I'm just going to back up because I think I have it close here. That limit could drop a little bit. And who's first in line? HV212. So I had an old version of this slide that basically said, we think you're super AGVs, but HV212 is tricky. That's still the case. So that's why the spectroscopy makes things complicated. Yes, thank you for asking that. Okay, I will be around, so if people have more questions, I'd be happy to take them afterwards. But thank you all so much for listening. I hope you enjoyed. And I will plug at the end here, we have telescopes that you can go look at. We have model telescopes, we have tactile astronomy, and the people at AstroTours have done an awesome job of making a card game of queer astronomers, and it's awesome. So when we wrap up here, you should all go have a look at that and look at all the hard work that the whole AstroTours team has done. And thanks.